All right, well, welcome everyone. Really good to see you all here for the first Talk2D seminar for 2023. But of course, before we begin, AM2D and Monash University wish to acknowledge the people of the Kulin Nations on whose land we are gathered. Today, we pay our respects to their elders, past and present. And I ask all of you to pay respects to the traditional owners on the lands which you are situated. And before I throw over to Naimeh as well, I just wanted to put it out to the group, to the Zoomverse, that if you have any suggestions about speakers for Talk2D or any suggestions or feedback at all about these talks, then please do reach out to me or to Naimeh. We'd be really grateful for your suggestions. Naimeh, I'll throw over to you to introduce.
Thank you, Phil. I think this is an exciting opportunity to hear about the latest in 2D materials. So with us, we have today Associate Professor Naimeh Naseri. She's from Sharif University of Technology. If you are not familiar with the university, it is the #1 university in Iran, and she's in the Department of Physics. Her research area primarily looks at new materials, 2D materials, and today we are going to hear about what she has done using these new materials and new physics in the space of energy and health systems. So without further ado, I would ask Naimeh to start her lecture.
Thank you. Thank you for introduction and also providing me such opportunity to have a talk in this group and for participation. My talk today is mainly about the role of layered materials in systems that involve the redox reactions for addressing health and energy issues. And I'm going to provide an overview and a summary of recent researchers that I have conducted and led in my research group at Sharif University of Technology. Just check. I'm not sure that I skipped to the second slide.
We can still see the first slide.
Yeah, I'm not sure what's the reason, but let me check again, Phil. It's the second, yeah?
Yeah.
Okay.
Switched across.
These research are conducted in collaboration with national and international collaborators worldwide in countries like Korea, Taiwan, Germany, Italy, and other countries. And I'm going to divide my talk into 3 different parts. But I try to focus on role of 2D materials in each system. The first is photo and electrochemical reactions, mainly water splitting reactions for producing the green hydrogen. And the second topic is about electrochemical energy storage systems, maybe supercapacitors and micro supercapacitors. I will try to focus on the role of layered and flake-like metal oxide structures for such devices, and ink development for inkjet printed micro supercapacitor. And the last topic should be related to some examples of biomedical applications of 2D materials, especially antibiotic performance of graphene oxide flakes, and also applying MXenes for electrochemical diagnostic devices. Let me start with concerns about green hydrogen production. As you know, that because of climate concerns and limitation of fossil fuels, we are searching for alternative fuels that could be clean. And the most promising candidate is hydrogen. with energy density at least 3 times than conventional fossil fuels. And there are some scenarios producing the hydrogen, and the most of hydrogen we use today is based on fossil fuel reforming, which is not sustainable method. So for applying more in the human life and industry, we should switch to another renewable resources. And 2 scenarios in this context is one direct solar assisted water splitting, which is called photoelectrochemical reaction. And another scenario is electrocatalytic water splitting, which happens in the conventional electrolyzer. And based on numerous roadmaps that are frequently published by different countries, which are pioneers in this research, there are some targets just adjusted for the cost of green hydrogen. For example, it's supposed to have $1 per 1 kilogram of hydrogen for the next decade. So it's vital to find a proper catalysis that could be low cost and also efficient for such transferring to industrial. So these 2 scenarios both involved with catalysis that should be efficient, durable, and stable. Could be scaled up and also have good selectivity. And there are many companies are searching for such systems and decreasing the cost of green hydrogen. Regarding this topic, photoelectrochemical reaction is considered as a more long-term route for obtaining green hydrogen as compared with electrolyzer coupled with renewable electricity. But potentially it could have less cost, and the reason is because it's more integrated compared with conventional twist technologies that the efficiency is limited by the efficiency of the electrolyzer and the solar panel at the same time. Let me just introduce the physics of such system. In the photoelectrochemical water splitting system, we have semiconductor material, as you can see here. Yeah, let me turn on my pointer. Yeah, the yellow layer here is the semiconductor material that faced with electrolyte, which is water. So depends on the semiconductor, N-type or P-type. We have upward or downward band bending in the interface of water because of forming a space charge layer at the interface. In this semiconductor nanostructure, electron hole pair are photoexcited because of interaction with light, and electron initiate a reduction reaction on the surface of contour electrode after migration in the external circuit, and the hole on the surface should initiate the oxidation reaction in the system, including N-type material, and for another analog was P-type included system. For both arrangements, the concern is about the stability of the material against the light, I mean the photocorrosion resistance, and also stability of the gauge photocurrent during the time. Optical properties of the semiconductor is very important. We are searching for semiconductor material with suitable band alignment in terms of the position of valence and conduction bands of these materials, again, as compared with reduction and oxidation levels of water in specific pH. Also, we should check charge transfer and separation gain of such systems, and enhancing the available surface interface between the electrode and electrolyte. recently, not exactly recently, 3 years ago or 4 years ago, we published a review paper in EUS. And in that review paper, we were dedicated to summarize a role of 2D materials in photocatalytic water reactions. The main 2D materials in such contexts are graphene, graphite carbon nitride, or transition metal decalcogenide, and 4 different roles could be considered for such 2D material with the junction of semiconductors, as they can enhance the surface area, improving light harvesting gain, and enhancing charge separation in the system, and also stabilizing the overall performance of the electrodes. One of the good candidates in this context is iron oxide in the phase of hematite. I mean, that has some advantages, like moderate band gap, which is well matched with solar radiation, and good band alignment, theoretical maximum solar to hydrogen efficiency. It's non-toxic, earth abundant, so it's not expensive. But at the same time, it suffers from some disadvantages, like poor electrical conductivity and short hole diffusion length, which limited oxidation reaction on the surface, and also sluggish oxygen evolution kinetics on the electrodes, and poor charge transfer and separation in such material. We started working on the hematite-based photoelectrochemical systems in 2018 with one of my former PhD students, Behrouz. He is now a senior researcher in Taipei National University. And we designed an electrode on the containing reduced graphene oxide and nanorods of hematite, and also nanobelts of hematite oxyhydroxide as a co-catalyst on the system. So he found a one-path system for producing such ternary composites, and we found that because oxygen containing surface functional groups on the RGO, this host could facilitate formation of iron oxyhydroxide nanobelts as a co-catalyst on the surface of main active material, which was hematite nanorods. And also the electrons can jump easily from the hematite to RGO, and then to the back contact, and then to the external circuit. So we can enhance charge separation in the system, and finally gain the photocurrent density nearly 3 times than the pristine hematite. We continued the work with doping the hematite with other elements, and found that 1% doping with titanium is beneficial for enhancing the charge transport in the hematite. And very recently, one of my students conducted a research to develop in situ electrochemical modification of surface of electrodes, in which that just before testing the photocurrent of the whole system, we sweep the surface of electrode in a cathodic direction for a special window of potential, and realize that we could have nearly 60% increase in the measured photo current. And the reason behind such enhancement was formation of defective and co-doped ultra-thin layer on the surface of the positive which was very homogeneous coating. This thin layer was co-doped with titanium and also with potassium. The potassium was originated from the KOH that was the electrolyte in the modification. And with this passivation layer, we could have a very stable photoanode, at least for nearly 100 hours. And we had improvement in injection and separation efficiency. And also more uniform potential on the surface. You know that surface potential fluctuation may hinder the charge transfer on the surface. So such modification could decrease this fluctuation, which is beneficial for OER reaction on the surface. Because this method is very easy and could be applied for other morphology, we can generalize this method for flake-like structures and layered metal oxides as well, which is a topic of our works in future. And Milad also works on the similar project in McGill University now as a PhD student. Applying to the material is not just beneficial for water splitting systems, but also for water treatment system. As you know that we are suffering from dyes like rhodamine B in the wastewater, and researchers try to degrade such pollution. So we applied RGO as a substrate for zinc vanadium oxide as the photoactive material, and applied the system for degradation of rhodamine B as well. So using DFT calculation, we realized that the band alignment in at the interface of semiconductor material and graphene is beneficial for charge separation in the zinc vanadium oxide and suppress the recombinations, and also such a porous and high surface host could increase the total available surface area between the dye and the solvents and also photoactive material. In another project, which is conducted by my former master students, I really was co-supervisor. In that research, Ashkan developed a method for the first time, which was microwave assisted. And during this synthesis method, in a one-pot approach, we produced graphite carbon nitride and also a non-particle of tin oxide at the same time on such a structure. And again, we benefited from the charge separation because of the such heterojunction for water splitting reaction. You know that another scenario for producing green hydrogen is electrocatalytic water splitting, especially when such electrolyzer powered by electricity from renewable resources. In such system, we have reduction reaction again on cathode and oxidation reaction on anodes, and but we have some catalysis on the electrode because you know that HER and OER both are sluggish reactions, especially oxygen evolution reaction, because it involves with transfer of 4 electrons for 1 molecule of oxygen. Of course, in terms of thermodynamic, such water splitting reaction costs for 1.2 volts, but considering the kinetics issue, it costs more than this value may be nearly 2 volts, and our research should be directed to find a low-cost and stable electrocatalysis and also efficient electrocatalysis that could be reduce such overpotentials. And you know that we are searching for catalysts that have optimal interaction with intermediate byproducts, and not weak interaction and not very strong, that makes the surface of catalyst toxified. In another review, we try to overview the role of 2D material for reduction reaction. In this context, mainly graphene and molybdenum disulfide are used widely, not just for water reduction reaction, but also for reduction reactions under the electrodes that are applied in solar cells, like dye-synthesized solar cells, for example. And there are some volcano plots proposed experimentally and theoretically for such catalysis that would potentially be applied on the anode or cathode in terms of the Gibbs free energy formation of intermediates, or also absorption of, for example, proton on the surface. As you can see that the most efficient candidates are expensive and precious, but we are looking for low-cost candidates. In terms of oxygen evolution reaction, cobalt oxide would be a very promising candidate, but it should be designed in a way that more active sites would be provided on the surface, and the stability of the catalyst also another issue. As I mentioned, we have two strategies to providing more efficient catalysts. One is increasing the intrinsic activity of the catalytic site, another is increasing the number of active sites. And in the latter, it's important to produce a surface that transport limitations can be suppressed, and the maximum number of active sites are accessible for the electrolyte. In this context, it's important also to have the tunable and controllable method for producing the electrocatalysts, especially in the higher scales, because scalability is another concern. And also it's better to fabricate a structure that could have a very high level of conductivity to facilitate charge transfer on the surface and show the layer to the external circuit. One of my former students started a research and a couple of papers published on this subject. We targeted cobalt oxide for oxygen evolution reaction, and we selected the electrodeposition method. First, we find that there is optimum current density and also deposition time for a galvanostatic approach in electrodeposition of layer-like or flake-like cobalt oxide. And fortunately, the surface was a mix of oxide and hydroxide phases, but the core was nearly metallic, so we had very good conductivity in the system. In the next step, we try to produce a hierarchical structure to maximize the available surface area. So we benefited from electrochemically reduced graphene oxide, and we provided a mixed paste with CNTs and some binders, and we tuned the composition of this paste and applied it as a host for next step, that was electrodeposition of cobalt oxide flakes. We realized that for a specific portion of RGO in the host, we could have not just flake-like structure, but nearly starfish-like structure with multi-scale roughness, and that could be named as a hierarchical structure. And the reason was that in such composition, we have an optimum amount of graphenic domain on the surface, which was more conductive than other parts, because other parts in non-graphenic domain in graphene oxide, or also in carbon nanotubes, we have surface functional groups that hinder the conductivity. So more conductive parts allow the formation of shoulders or bumps at the first stage of electrodeposition. And then on the shoulders, we can have a smaller flake, which finally led to the minimum value over potential and also minimizing the charge transfer resistance. Okay, let me to switch to the second topic, which is related to applying metal oxide sheets for supercapacitors. As you know, supercapacitors are attractive energy storage devices because of high life cycle, good power density as compared with the batteries, fast charging, and good safety. In the supercapacitors, instead of typical dielectric, we connected to electrodes ionically with the aim of the electrolyte, and two different mechanisms could be considered for energy storage, electric double layer, and also to the capacitive behavior. We started our work in this area from nearly 2014, when my former PhD students, Mohammed, fabricated a device based on cobalt oxide nanoflakes again. And now he's a senior researcher in National Taiwan University and collaborates with us very tightly. In this project, we electrodeposited a thick layer of cobalt and then tried to anodize the layer to produce a porous film, and at the same time, because of anodization reaction, some flakes form on the surface of porosities. So we had two layers in junction with each other by one-step anodization, and we find the optimum voltage for such anodization process, and find that we should have an activation process, as you can see here, after nearly 1,000 cycles running such devices. The capacitance increased because of the all porosities were accessible with the KOH of an electrolyte, and considering the stability of the system, we had after good stability after nearly 4,000 cycles. Using a semi-empirical model, we tried to find about the portion of the contribution portion of each part. One part was flake-like layer and another was porous anodized layer. And by this model, we realized that, as you can see from the coefficient of K1 and K2, that the portion of the porous anodized layer was much more than the flake-like structure because of higher thickness. And to increase the contribution of flakes, we should have larger flakes in terms of lateral size than this one. So we changed the strategy, and now we design another host for growth of cobalt oxide flakes. We synthesize a porous and sponge-like graphene skeleton, which is very conductive, and the method was template assisted using PMMA particles. And inside such sponge-like structure, we again those cobalt oxide nanoflakes, cobalt oxide and hydroxide composite phases actually. And we try to control the performance of overall electrode by changing the electrode deposition condition. And as you can see, we find that in a low amount of loading, we don't have any pseudo-capacitive active material, and in the high amount of loading of flakes, actually the maybe we block the porosities of sponge-like graphene, and because of low conductivity inside the flakes, the overall capacitance reduced, but we found the optimum condition for growing such flakes inside the sponge-like graphene. And this device, both in asymmetric and symmetric configuration, delivered very good capacitance retention after high number of cycles. Another subject we were interested in was printing the supercapacitors, but as you know, during the fourth industrial revolution, some topics like Internet of Things and smart sensor are very attractive, and such systems needs a small power supply, small size power supplies with high power densities, and preparing supercapacitors in the micro scale design would be beneficial for powering such devices. So for preparing micro supercapacitors, it's better to think about flexible and foldable electronics. And maybe it's better to be disposable even. In this context, printing methods are very beneficial, and we have a variety of methods, but we were interested in inkjet printing, especially because of high resolution that this method could give us. For example, when we want to design a micro supercapacitors in interdigitated form, so we need more resolution. But for inkjet printing, we need to develop inks, and these are the concerns about rheological properties of inks in terms of density, Weber number, Reynolds number. We should avoid satellite droplets. At the same time, we should have concentrate ink to avoid multiple printing process, which is time consuming. One of my postdocs, Ali, started this research field in my book, and there is a review on inkjet printed 2D materials for supercapacitor devices. This method is adaptable not just for active material loading, but also for current collectors and also electrolyte printing for full inkjet printed devices. But in all research, we started with manganese oxide flake-like structure using a simple hydrothermal method, and these flakes were connected in a flower-like structure with a good size, well below the size of nozzles of printers to avoid the clogging effect. And also we try to develop the ink without adding any additives, because you know that additives are not basically active material, electrochemically active material, and they could have negative effects on the electrodes. At the same time, we prepared silver nanowires with very simple method. We selected paper, cellulose paper as a substrate, and in the continuing research, we are going to join this on-paper supercapacitor with another elements. But the more important for us, it was because it's disposable. Actually, the device printed on the paper could be disposable. For current collector, we developed the current collector based on graphene sheets prepared by LPE, liquid phase exfoliation on it. And first, the surface of cellulose paper was modified with sheets of graphene to have more uniform surface, and then silver nanowires were loaded. And now the current collector was ready. So we printed the manganese oxide, manganate oxide by inkjet printing method. And the device was very good in flexibility and foldability. And the challenge we had for solid state supercapacitor was applying gel electrolyte. You know that it's issues in terms of diffusion at the interface of gel electrolyte with the electrode material. So this was the reason that hinders the Coulombic efficiency or capacitance retention, but we are still working on this subject. But for the first work, as compared the results in the dragon plot, you can see that the result is acceptable as compared with other graphene-based or MXene-based systems that are inkjet printed. In another work, we try to inkjet printed devices based on cobalt hydroxide flakes, and to avoid the restacking of such flakes, as we employed a cobalt oxide nanocubes inside the system. Both of such composites have electrochemical activity for energy storage, but presence of cubes prevents stacking of the flakes. In this work, we try to develop the ink based on water because it's not hazardous, it's safe. And we use ethylene glycol for modifying the density, and again, we had very flexible in bending and folding devices. So in the next step, we modified, we used this composite ink to modify LDH, nickel cobalt based LDH, and the capacitance was nearly 30% enhanced with addition of this ink to the LDH system. I'm not sure about the time, but I hope to can overview some biomedical example applications as an examples in my group very fast. You know about the antibacterial properties of graphene oxide sheets. According to World Health Organization, we should find alternative antibiotics for some bacteria. For example, Staphylococcus aureus has a high priority in this report, and because they are very antibiotic resistant, people usually look for another types of antibiotics, and in this field, 2D materials, especially graphene oxide, because of less toxicity, again, as compared with others, is could be potentially good candidate. But in this field, there is controversies because the results strongly depends on the chemicals and surface functional groups and the size of the flakes. And the most important is the test protocols and the standards people are going to use. So in another research with my postdoc and my master students, we prepared 7 classes of graphene oxide sheets in terms of size, from 100 nanometers to hundreds of micrometers, and we found that the interaction of the bacteria with the graphene oxide is strongly dependent on the size of bacteria, on the size of graphene oxide sheet in the suspension form, because they developed a suspension, not like wound dressing or immobilized graphene oxide. And in this format, using minimum inhibitory concentration and minimum bactericidal concentration measurements, we found that the mechanism is just wrapping and isolating the bacteria, and so it has bacteriostatic effect instead of bactericidal effect. And we developed or study from the in vitro to in vivo model. We used 6 groups of rats and try to evaluate the mechanical properties of the healed wound on the skin of rats, because you know that the rate of wound healing is very important in such for such treatments. And here you can see we have 6 groups control and another 2 control system that just cured with DI water, and another group was infectious but without injection of graphene oxide. And we have 3 main groups that with different doses of graphene oxide for the doses of 16 microgram per milliliter, and also for 8 and 32. We have positive effects in terms of mechanical properties of the skin, cured skin. Also, in a complementary work using a molecular dynamic simulation, found that interaction of bacteria with the graphene oxide is strongly dependent on the membrane of the bacteria. Staphylococcus aureus is a kind of gram-positive bacteria with peptidoglycan structure on the outermost shell, but for example, PA means some kind of pseudomonas, which is gram-negative bacteria with lipopolysaccharide on the surface. And molecular dynamic methods showed us that the interaction of bacteria is dependent with the cell membrane, and gram-positives are the most suitable for kind of bacteria to interact with graphene oxide. And for gram-negative, we have just loose half-covered method. And the results rule out the knife-like structure, knife-like interaction. Just it was wrapping, but maybe for smaller flakes we could have cutting. And the last example is about the MXenes. You know that MXenes have good conductivity and hydrophilic property, and also it has multi-element components inside when it's after etching, and also doping with nitrogen. We could have a strong binding with some other elements. In this work, we applied MXene as an immobilizing host and then put monos on the surface and applied as a diagnostic, electrochemical diagnostic device for bacterial detection, and also developed a filter for separating the E. coli from the wastewater. I think that time is over. So let me finish. I just try to summarize some of my research works that are involved with 2D materials, and just providing a very fast summary. And now I should thank you to my collaborators in Home Institute, and also worldwide in National Taiwan University, in Korea, in Germany, and Georgia Tech. And also I should thank from funders in Iran that support us such research. Okay, I'm here for any question.
Yeah, thank you very much. And this was a really good overview of what you have done. Many years of research, I can imagine. It's not just a couple of years of work. So congratulations on being able to conduct work of this scale. I would probably ask anybody from the audience to ask questions, and maybe then I can have a bunch of questions for you.
Hey, Naimeh, thank you very much for your talk. So I have a question on the supercapacitor side. So you have shown that there's the device can achieve 20,000 cycle. So after 20,000 cycle, what happens? Like, can you comment on that?
Yeah, let me skip to that slide. Let me check. For which system?
This is supercapacitor work.
No, which one? The cobalt based or
Cobalt.
cobalt
flake.
Oh, yeah, this work you mean now?
Yes, yes. So after 20,000 cycle, what happens to the cell?
Actually, we didn't continue the stability test. We did it just maybe 2,000. I cannot remember exactly, but maybe few cycle more than this value. We didn't cut the window to just report that. It was very stable for up to 20,000. And maybe we continued for 100, 200 more, not more than this, because at that time we were faced with such technical limitation with our devices in potential. So I cannot comment.
If you could comment on the failure of the device after after the unstable region. That would have been interesting for me.
Yeah, I will check with my students if he had. I will come back to you. But as I remember, because we electrodeposited the main electrodes and then prepared the cell. In some cases, we faced with loss of material, and they separated from the current collector, I mean. But in this case, I'm not sure. I will come back to you.
I think.
Yeah, I have a quick question as well. Since we're on this slide, I was actually interested in asking about the activation process for this device. Could you maybe explain what that entails?
You know, we have multi-scale process structure, yeah? And the whole process should be accessible by the electrolytes. And the electrolyte is water-based, mainly including the potassium hydroxide, for example, yeah? So it takes time to wet all positive in the mesoscale, for example, inside the electrode. When we put the electrode inside the electrolyte, at the first second, it's not possible to benefit from outside, but repeating the cycle number for a while, we can activate the all positive. It's the reason of increasing the capacitance for example, after 5,000 of cycles.
Right.
It's probably it is probably have to do something with the diffusion of the electrolytes into the pores.
Yeah,
we see that often in our experimental data, but not for 5,000 cycles. Usually, our activation or whatever you call it, it's a few hundred, maybe 200 cycles.
Yeah, in which sweep rate you mean? Because we had a very high scan rate here.
Oh, okay. Yeah,
when a scan rate is high, usually the number of cycles should go up. Yeah.
Correct. Yep, that makes sense.
Yeah.
I have a small.
Go ahead.
I have a small question. In your manganese, first of all, thank you. Very good, informative work. So you have presented some manganese oxide work, and you captured the delta phase. You have grown. So can you please tell us how you have grown that delta phase and why you are interested on that delta phase? In your next slide, you have mentioned delta phase.
The delta phase of manganese oxide, you mean?
Yes.
This phase is also active in terms of reaction. There are very numerous works considering this phase of manganese oxide. I'm not sure that I could understand your point. We also alpha and delta, both of them are included in research in the field of supercapacitors, I know, but I don't know what's your point in this area. You mean it's not it's not as active as the delta phase?
Yeah, you have mentioned next slide. If you can go to the next slide.
You mean that this dragon plot, yeah?
Yes, there you are mentioning the delta phase.
This delta phase is another work, or work is the red one?
The red one is your work, right?
Work is this red one. So we have a delta phase with more capacitance, delta phase with less capacitance, and the issue that is different in this system is mainly interaction of the electroactive material with the electrolyte. We suffer from the gel electrolyte in this work, and this was the reason that limited our capacitance and power and energy density, not the phase of manganese oxide.
I have a question on your biological work. We in our research group are interested in anti-fouling coatings. Now, what is the relationship between antibacterial and anti-fouling? Is there a common mechanistic understanding that you can translate from antibacterial to anti-fouling?
Actually, it's hard for me to provide a comment in this context because my focus was just regarding the interaction of such 2D material with bacteria. And in case of anti-folding material, I'm not sure. Let me don't provide a non-precise comment. Sorry.
It's all right. So the hematite work, which is also quite interesting.
Which material? Sorry.
The solar photoanode, which was made out of hematite.
Yeah. Yeah, hematite is very attractive. Yeah, let me switch here, maybe here. Hematite is very attractive. It's earth abundant. Yeah.
So what is the state of the art in terms of photoanode material in real life devices? Are you aware of devices?
For hematites, nearly see in terms of photocurrent density of such photoanode, nearly 6 milliamp per square centimeter is a good record. But this is usually not for pristine hematites. We should include some components. For example, of course, we need co-catalysts on the surface, hematite oxyhydroxide or other kind of LDH on the surface. We should dope hematite also, to maximize the surface interface and also passivation layers and other tissues. But if all components are came together, 6 milliamp is the good record. Yeah.
All right. There has been some like hematite is in general, it is not a layered or it's a layered material, but with strong bonding between the oxide layers, right? There has been some work where this sort of non-layered materials have been converted to two-layered, samples, and their properties have been measured. There are quite a bit of differences in their properties, actually. If you have hematite in the form of bulk hematite, because what you're having here is probably mostly bulk hematite.
Rod-like.
Okay.
Sometimes, it's a preferred morphology, usually formed in the hydrothermal process.
Yes.
If we don't use any additive or surfactant in the system, because to avoid residue on the final photoanode mainly, it's the preferred structure. If you follow, for example, the works by Sivula and Gratzel in EPSL, they also developed hematite for tandem cells.
Correct.
In this format,
Very interesting, Amasa. This is probably a nice area to be thinking about.
Unless there's any other questions, we might end it there anyway, because we are at time. But Naimeh, again, like Mainak said, thank you so much. Such a broad scope of research and of course spoken so confidently and just really interesting. So thank you very much.
Thank you.